Well, it's 4. I might as well get started. Can anybody not hear me? All good? Alright. I'll take no answer as a yes. Today we talk about one of my favorite topics, which is animation. And we'll also finish up networking, which I prepared slides for last time, but we didn't get to them. It'll be a relatively short discussion because we don't actually have a networking assignment, so there's no reason to go too in the weeds. So today I'll make some quick assignment 7 comments based on some questions people had. I mentioned that we might need to use some Friday sessions for the more advanced topics. Definitely not this Friday, but maybe one of the next few or 2 of the next few. We'll do some quick practice problems for the midterm assignment, and we'll talk about networking, and then we'll talk about animation and a couple of different methods. The reason that I started animation now instead of going into the AI demo that I had planned was because the AI assignment is going to be extra credit way at the end. The IK assignment is assignment 9, so and you do need to know animation to be able to do IK, so I figured that it made more sense to do animation first. By the way, can you see my mouse?
Yeah.
Alright, cool. After we finish animation, then we'll do some AI demo. So some quick notes based on some questions people had about assignment 7. I did make a very bare bones version of the algorithm in the assignment so that the comments don't make it any more confusing. This is a formatting thing. In the Kennedy 93 paper, they write that total score is, well, you can't see it because of this annoying Google thing, but it says like 1 plus 2 plus 3 times 3.74. It looks like it's only the 3 times 3.74, but it's actually all of them. So it's just a weird formatting thing. I don't know why they thought that was a good way of formatting it, but that's how it is. It came out in 93, so. For SSQ, a total score that's more than 100 usually means that the user is too sick to keep playing. So normally we would pull the user out if we find out that they're getting too sick. A lot of the times for longer user studies, you might do an SSQ multiple times throughout the simulation, which is what I did for one of my papers. I had like 3 levels, and between levels they would fill out an SSQ, and I would use that to determine if people were getting too sick. I actually didn't really have, I think I had maybe 1 user who got sick out of like 46, so it wasn't too bad. A couple of people were confused about the p-values. It is actually possible that p will be basically 0. Remember that this is only to 3 decimal places, and a p that's less than 0.05 is significant, and the lower that p is, you can think of it as the more significant it will be. That's not always true, and p is a really rough estimate that we use in psychophysical studies because, you know, it's hard to accurately measure perception, but it is possible for it to be almost 0. You should be able to figure out what that means. It's just, I mean, it should be pretty self-explanatory. If p is closer to 0, then it's more significant. Anything less than 0.05 is considered significant. In machine learning, they don't really use p because it's not an accurate metric, but in psychophysical studies, it's as accurate as we need. So some quick practice problems. I mentioned this in the intro slides, and I think in the audio slides, that you might have a question like this. Say that you're some VR design consultant and I'm some indie dev who wants advice about making a game VR compatible. Mute yourself. I might ask you questions about, or you would answer with considerations about, you know, how would I actually make my game VR compatible? So for example, let's say somebody wants to make this Skyrim-like combat game that has Diablo-style loot in the Oculus Quest. I might ask you, how do you handle locomotion, audio, and the API itself, and so on, like the game engine. So I might say, in terms of audio, you might want to use filters because propagation is hard on the CPU. Also, propagation is not even compatible with Android, which I think I mentioned before. And filters for a game like this, maybe you just want the feeling of being in like a cave versus outside. So filter would do a good enough job of giving you that feeling that you're in a different environment. You might want to think about pros and cons of Unity or Unreal in this case. So like Unreal, for example, is better integrated with the Oculus API. It also has better cross VR platform compatibility. But Unity is made for mobile devices, and the Oculus Quest is a mobile device, so it might have much better performance. So these are just some pros and cons to think about. As far as locomotion goes, because it's a real-time fighting game, and if you use a method like teleportation, for example, it would almost be cheating. You might want to use some kind of continuous locomotion method like redirected walking, maybe the most simple joystick motion, assuming that you restrict their field of view so that they don't get sick. You could do motion compression, although it's overkill. If you remember motion compression, it's that paper where you fold the entire space, the entire virtual scene into the physical space. But these are just some things to think about. And you might want to think about how would they test if the method works. So you could do a comparative study that measures psychophysical things like presence, sickness. You might have some custom questions that measure, for example, does your locomotion method cause distance compression, things like that. For the more objective measures, you might want to have some group that has sensors, and you can measure like their temperature and sweating and things like that. Any questions on this? No. I have another practice problem, but it's very different. So in the second one, I mentioned that I might propose to use some really bad user study that I want to use to test a VR feature, and you would tell me like the flaws and how you might do it and why. So think about sources of bias and randomness that might poison your data output. So for example, we mentioned before that there were plenty of flaws in the assignment 5 study. For example, 4 users is not nearly enough to be a decent sample size, and if you have 4 users, there's a large amount of variance. It's not really standard distributed and so on. So you need at least 10 to 15 users per combination of independent variables. So in assignment 7, I think in assignment 7 you have a high distortion and a low distortion group, for example. But I actually merged 2 independent variables together. I merged the high distortion group has like 70% gain and like 30% loss or something. If you were to split those into 2 independent variables, then you would have to have 4 groups of 10 to 15 users, because you have two gain values. You have the regular 30% and 70%, and you have 2 loss values, the typical 13% and the really high distortion of 30% or something like that. I mean, does that make sense? Is anybody confused about that? Why, I mentioned why already. The users generally shouldn't communicate with each other. So for example, when you guys were in the lab doing your tests, your users were talking to each other and saying what they felt about the simulation. Generally, we wouldn't do that. We would, because you can, I mean, it's like cheating in a way. Users learn more about the simulation from other users, and it can cause some amount of bias once they're actually in the simulation. The proctor should not ask questions directly, because there might be other forms of bias. So a lot of you just ask your subjects each individual question. Normally you wouldn't do that. You would just put them in a room with a survey. The proctor generally shouldn't even be present. So you might want to put the person in a room, close the door, and just stand outside and be available for any questions they have. There shouldn't be other sources of distraction, so not multiple studies happening in the lab at the same time. You might want to avoid wires in a locomotion study. And we also generally try not to intentionally make people sick. This would cause problems with the IRB, which there's some, I mean, it's Institutional Review Board, they approve studies and things like that. And if they learn that you're intentionally trying to make people sick, they will probably not let you do the study on campus. But this is we'll talk about research in VR much later in the class. You might want to use masks on your headsets, and even more recently. So, any questions on this? All good. Is anybody confused about any of the class material? Alright, I'll assume no then. More or less how I'll grade it is, it'll be pretty similar to the non-technical part of the regular assignments. The answers might be pretty subjective, so the grading again will be based on completeness and if you actually thought about the question and consider different methods, and if your considerations are more or less correct. Like, for example, with these game engine comparisons, some of it is just subjective, and it's up to you. Like, if you think that, if you think Unity is an easier, for example, if the client is a very new game developer, you might want to recommend Unity. Like, for example, they're a CS undergrad who just graduated or something. Maybe Unity would be better. I don't know. There are a lot of different ways of answering the same questions. I think that's it for midterm assignment. If there are no questions, I'll just move on. Last time we didn't quite get to it, but I was going to talk about multi-user applications, which are essentially the next step after crowd simulation. So for a multi-user simulation, we might treat other players as if they are virtual agents. And the problem here is networking. So how do you send data about one player to other players? And there are a few different ways of doing this. I have a lot of visuals in this presentation, but networking isn't the most visual thing in the world. There are a couple of different ways of doing networking. There's a networking class if you're really interested in it, but for centralized networks, you would have one computer on the network that is the boss. For a distributed network, you might have one computer that is like the super boss, and it delegates to some other computers which maybe are the boss of their own individual environments, like how franchising works for McDonald's and those places. Then you might have decentralized, which is just peer-to-peer and other connections like that. We don't really see decentralized much in games, so it's not worth talking about, but here are some images that show this, and if you're interested, there's this link that has a pretty good explanation of how this works. And I also have examples relative to games which might help your understanding. In games, we often use the client-server model, and the idea here is that a client can only make changes that affect other clients by asking the server to do them. So the server, let's say that this is like a centralized network and you have a server who makes all the final decisions. Clients can't actually make any final decisions which affect everybody, so they need to ask the server to do everything, and the server needs to approve their decisions. We use remote procedure calls to communicate between clients and servers. The idea, remote procedure call, I think, is a pretty good naming convention. It just means it's a function that is on a remote device that you're calling. So you're calling some function that is on a totally different device. A server has a couple of options for how to actually delegate to other users. They can do it unicast style, where it updates one specific client. So, I don't know, I had some examples here. For example, a settings change. Like maybe you have a preference in your settings and say it's multi-platform. So for example, if you switch between a 3DS and a Switch and you're playing, like, I don't know, some game that's multi-platform that exists on both platforms, and you change a setting that only affects you, a unicast request will update it for you on other devices but not other clients, because other clients don't need to know your personal settings, like, I don't know, mouse sensitivity or whatever. There are tons of examples of settings that you can think about. The server can multicast, which is one of the more common ways of doing it. So it tells all the clients update certain information. So for example, if I move in the game, all the other players should see me move. So the server, if I'm the client that moved, like let's say that I hit W and I move forward, I actually won't move forward locally. What will happen is that I'll ask the server to move me forward with respect to everybody. If, for example, a player activates a trap like in Overwatch or something, all of the other players should see it get activated. For things that get updated all the time, like player position, we might not want to keep calling things on the server. We have this other factor called replication, so we might set the player to be replicated, which means that they'll just be updated all the time. The details of how this is done are not super important for us. Usually, from the perspective of a single game, like if you're in Call of Duty or something and you have a couple of people in the game, we think of this as centralized. So one person gets chosen to be the server, or the server is just some third-party observer. And everybody else is asking this one person to update them. So I think Call of Duty does it this way, right? Where one person always gets chosen as a server, and I don't think there are any dedicated servers, so it's pretty much always a centralized network. But a game like Battlefield, I guess, has servers all the time. For a much bigger multi-server multiplayer game, we have more distributed networks. So, for example, the Battlefield example, where I guess Call of Duty, by my logic, Call of Duty is also distributed. That would make sense to me. I was thinking of something different. Anyway, in a bigger game like Call of Duty or Battlefield, you have a server that is controlled by the company that runs the game, essentially, and it keeps track of progress. So, for example, as you upgrade your weapons and get XP and stuff like that. And each individual game will essentially be centralized, but they will eventually push all their updates to the super server that is controlled by the company. So, just some quick visualization. If this, I think, is with respect to time. So, if who's that?
Hey guys, what's up?
Mute yourself. I forgot what I was doing. Did the screen turn black? Is it good now?
Yeah, it's fine.
Okay. Over time, let's say that some functions are called, or you have some animation in this case. The clients won't update things directly. What they'll do instead is send the request to the server, and then the server will say, oh, okay, now you can move. And the server itself handles the actual movement, not the clients. And if you think of it as like a client being over here, the server would also update it for them. And here's some other examples. So the player does something in the game. So the player tells the server that I did this thing, and then the server approves it, and then they send the new information to all the clients, and they tell the clients to update themselves locally. So just something to think about. Why shouldn't you just multicast everything? So if you remember, multicast tells everybody to update all the info. Why couldn't you just multicast everything? Isn't that isn't that the best way of ensuring consistency? Anybody in a networking class who wants to share their opinion on this? Okay. There's a latency concern. So every piece of information that you send has some latency overhead. And for mobile devices, which have weaker network cards like the Quest, this might cause a ton of lag over time because network cards can only receive so much information at once. And information is essentially queued most of the time. So if the network card doesn't have as much, if it's not as strong, that it can't handle as much data at once. So it needs to handle it in sequence, which means that there's more lag. There's a relevance concern. So clients should not know all of the information about other clients because this could lead to cheating or hacking. So if one client locally, without any server information, can figure out where all the other clients are, then they can essentially use that to cheat. You could do, I don't know, there are tons of hacks related to this. Like you could auto aim at people because you always know their positions and things like that. In VR, this is even more of a problem with VR multiplayer games because there's even more flexibility. Like if locomotion is not handled well, people can push themselves through walls and things like that. And pushing themselves through walls is already a bad thing, but say, for example, that they can see through the wall into another part of the scene, that leads to them learning unwanted info. There is some processing overhead that comes with processing any data. So if the server keeps sending out remote procedure calls telling the clients to update everything, the client is the one that ultimately needs to do this updating, which takes some amount of processing. So again, mobile devices have limited CPU power, so we try to avoid having them use their CPU too much. And VR has other extra considerations, like there are more transforms that, well, VR has transforms that need to be updated more often. So if there's a lot of lag in the motion for a VR character, it will hurt immersion. There are more things that we need to network for VR characters, so they have their physical space, they have each of their hands and any other trackers that they use. There's the head itself. All of these things need to be updated at a decent rate. So we want to try to avoid causing more lag than is already going to happen with VR. And as VR becomes more and more complicated, there is even more information that needs to be networked. For example, say we have more accurate avatars, whether they're customized or if we reconstruct the real person, that's way more data that needs to be sent to other clients. If we have accurate skeletons, like say for example that people can wear some suit that will keep track of their entire body position, you would also need to network those. You would need to network each part of their skeleton, each of their joints, and so on. And yeah, we haven't we're going to talk about animation today, but each of your individual joints needs to get networked. So it's just way more data that needs to be handled in VR. So we need to think about this. Some other optimizations that we think about: we can decrease update frequency of certain things. We can not network certain things, or we can ask only the server to update things. There's a reason that server computers generally have tons more CPUs than we do. Like our computers in the lab often have like 24 to 36 cores. You can network less detailed versions of things. You can not network things that aren't visible. So for example, if another player is behind a wall, for example a VR player, I might not need to know exactly where their mesh is. So this is something that the server itself can figure out. The server can say, okay, well, I know this player moved, but maybe not everybody needs to know where they are right now. So that's something you could think about. You can not network things that are far away. So in graphics, we have level of detail where we render something with lower quality if it's way too far from the screen. You can do the same thing with networking. And networking is hard, which is why it's a field in itself. And it's also why I'm not going to go into details related to it. It's also not very well understood. People they blame everything on netcode. Netcode is really vague and it's caused by a lot of things. But people always say, oh, the netcode is bad. More often than not, it's just an excuse for being really bad at the game. But, that's how it is. In game engines, since Unreal was already designed for a multiplayer game originally, it already has a very strong networking foundation. So almost everything in Unreal has built-in networking options. It's actually one of the reasons why actors in Unreal use so much RAM, because they already have so many of these built-in networking functionalities. And there's a lot of customizability and strong features. So usually when people make multiplayer games, if they want them to be good, they'll use Unreal or some other engine that's made for multiplayer. I'll show you some examples of some of the networking API in a bit. By the way, this is the last non-visual slide. Unity, mute yourself. I muted him. Unity had a built-in API called UNet. It was deprecated completely as of 2020.
I'm getting a lot of echo.
Yeah.
That's me. That's probably me. I'm going to mute myself.
Just mute him.
I mean, I muted him locally, but it doesn't matter. He muted himself. Anyway, Unity had a built-in API called UNet. It was deprecated completely in the 2020 version because it was inconsistent. Its usage was inconsistent. It had very limited features. It was really badly and inconsistently documented. And I think the only reason that they kept it for as long as they did was because people relied on it. But I think as of 2020, they were just like, we can't put up with this anymore. And they've been trying to refactor it, I think. Historically, Unity devs tried literally anything else. So for example, a lot of people use this thing called photon unity networking, and this is a pretty good API actually. But even so, the setup itself tends to be a lot harder in Unity because it doesn't have that many built-in functions. There's this thing that we'll talk about eventually called the data-oriented stack. It seems like a really good way, for people who know Unity already, it seems like a good way of doing efficient many-user networking. I think it's still a work in progress though. The data-oriented stack was meant to make things that are replicated over and over really efficient by putting the data itself very close to each other. So for example, all the characters that should be networked at the same way. So if you have hundreds of like, I don't know, say you're doing crowd simulation that's networked. If you have hundreds of AI that are doing the same thing, calling the same functions, you might want to pack all those functions in the same data space or something like that. Anyway, in Unreal, you network actors. So for an actor, you have replication information. So you can decide who this is relevant to, how often they should update, whether or not they update at all. Individual components also have replication. So for example, let's say that, I don't know, let's say that locally the user has a much more detailed hand than what other people see. Then maybe you want to replicate the less detailed hand instead of the more detailed one. That's just an example I can think of, I guess. And you can also network functions themselves. So for example, if you want a function to get called to everybody else or to the server or to some other specific person, like this is already built in, and you can choose some options like this function is only local. So mathematical functions, for example, would only be local. You could multicast it. Remember that clients themselves can't actually multicast because they can't affect other clients. So generally what a client will do is call a function that is run on server, then the server itself will call the multicast function or something like that. Anyway, this is not important for us, but it's something to think about. Maybe at some point, if people are interested enough, we can do some practice exercise on networking. But anyway, animation, the more interesting topic. Like I said last time, animation is one of the things that is most lacking in modern VR and just in modern games in general. It's definitely been getting better. It's not particularly well understood. There are a lot of methods and considerations in animation that people just don't know to make. It is becoming very profitable, and there are a lot of different cool methods, and I think this is a much bigger and more varied field than most people realize. So, example that I like a really bad animation.
Wait, see, he said you're back!
Can you hear audio?
Yeah.
I was loading that.
Georgie has parrots.
This is a really good example of bad lip sync.
You're back!
Yeah, I killed that guy.
See, he said you're back! Alright.
They're like, alright, what shape does the mouth take when you say a B noise? A B. And they go, alright, guys.
Like this.
Alright, what about a T noise? What face do you make for a T? Yeah. Oh, there it is. That's T. Yeah. So if you're gonna go to the TP, it'd go. Yeah.
Splendid. Splendid. Money lenders.
So yeah, I just like that video. So for VR at least, some things to think about. First, this Job Simulator is a really old VR game, and Boneworks is a very new one. So quickly look at these videos and compare the actual body representation. You'll notice a couple of things in Job Simulator. For example, when you're holding the cup, your hand becomes the cup, which is kind of weird. Your hands are really simple, low poly, not animated too well. You don't have arms. In Boneworks, you have arms, and you're interacting with things, and the motion's a lot more accurate. In this case, compare the physical interactions. So this is in Rec Room, which is another very old VR game, and I don't remember what they're trying to do, but you can see the physics are, they're not great. In fact, in this case, I think they're specifically trying to break the physics engine. This is Half-Life Alyx, which just came out a few days ago, and you can physically interact with basically everything. So what makes these games different from older VR games? And sure, the graphical quality itself is better, and you have bigger companies that are supporting these, but there are actual fundamental differences. So something to quickly recall before we go into this discussion is I mentioned this paper way back when we first started talking about VR. It's an Oculus paper that talks about avatars. So the elements of an accurate virtual avatar are good visuals. So from your perspective, your visual representation should be good. You should have good audio, and we've already talked about audio, but you have spatialized sounds, and you can have propagation and things like that. And then there is movement. So you should have accurate physical body gestures. And gestures might not be the only important thing. There's also just the latency and things like that. So what makes these games different? Like I said, the graphical quality is better, but in games like Boneworks, Asgard's Wrath, and some of these newer games, the body itself is actually represented. Despite the fact that you only have controllers and a headset, they can still make strong predictions about where your body would be given only your hand locations and your head location. Does anybody have any? I'll give you like 5 seconds to think about it. Do you have any idea how this is done?
Is your height taken into consideration?
It is.
Like, does the game ask you like for inputting that?
Yeah, most games ask. Well, I think the Quest itself, most calibration setups ask you for your height nowadays. So that's part of it. The height is also gathered from the game itself. So, for example, the maximum heights value, like in Unreal, is your maximum camera Z, for example, is a good approximation of your height as well, because your camera can't really go any higher than you are, if that makes sense. So yeah, that is one way of doing it. Many other ideas of how they do this. No, it's okay, we'll talk about it anyway. They do this through skeletal rigging and inverse kinematics. So actually the head height thing is something that's factored into the IK. Inverse kinematics is something that's been used in robotics since forever, basically. I mean, robotics is hardly a field without IK, but more recently IK has been expanded to tons of other fields because it's essentially a very strong set of methods that let you predict information about other orientations geometrically. And so, again, well, we talked about the actual body representation, but there's also physical interaction with most of the objects that are in the virtual environment. And again, IK comes into the equation again because if you don't have decent inverse kinematics to predict where other parts of your body are, you won't have good collision meshes. So, for example, let's say that in the VR game you want to be able to get shot in the arm with an arrow. Half-Life Alyx is a cool game, but it actually doesn't represent your body all that well. So, it's essentially a capsule instead of an accurate body. But with a game like Boneworks, I think that you actually can get shot in specific places. Even if they don't know specifically where your real arm is, they can predict it. So 3D animation is, I know I mentioned IK, but we won't get into that just yet. 3D animation is more or less a prerequisite nowadays to understand why it works. It's related to something called skeletal animation. And in the reverse order of how you figure these things out. So if we want to learn about IK, we need to learn about skeletal rigging, which is a part of skeletal animation. And to understand why we use skeletal animation, we'll talk about that. And to understand why we use skeletal animations, we first have to understand other animation methods and why we don't use those for these things. And skeletal animation is a good thing to know anyway, because to animate non-player characters, like any other human character or any moving character at all in the scene that's not you, you still need to know how to do skeletal animation. There are other newer methods that we use for more highly detailed characters. So to quickly define what 3D animation is, in your games, most of you, at least, have been using static meshes, which are 3D models that always look the same. So your collectibles are always the same object. They don't do anything. They're just objects. You can move them around, but they're not being animated or anything. They're still the same static shape. But some things do actually require motion, so a human moving, talking, etc. Some motions are predefined. So this jump, for example, is predefined. It's always the same cycle. We call loops of the animation a cycle. Some motions are described with graphs. So for example, if you want to describe some animation in which you can go from crouching to walking to running to sprinting to any of the other states, you would need a graph to describe that. So for example, let's say that you sprint, but you sprint into a wall basically. You might want to have some other state in the graph that describes you getting hit or you just stopping short. Some motions are physics-based or constrained somehow, so ragdoll physics like this one, or inverse kinematics, these are physics-based. And animation methods just describe all of these motions. So we'll review a couple of different methods, such as geometry caches, simple transformations, blend shapes, skeletal animation, and finally we'll get into IK. So a lot of people in the class I think had some kind of graphics background already, but maybe in 2D graphics. Geometry caches are essentially the 3D equivalent of 2D sprite animations. So you essentially save one mesh for every frame of the animation and you swap between them. So in this case, a frame would be the segment of the animation. So for example, if your animation plays at 120 FPS, and maybe a cycle of your animation takes half a second, you would need 60 frames to describe that at that frame rate. You would store all of these frames in a single file that would, it stores information about how you swap between them. In 2D, we have videos that do this. So, for example, any of the standard video formats are essentially swapping between frames. In 3D, we use different formats, which essentially do the same thing. They just swap between meshes. So the most common way of doing this is called Alembic. It's this file format that was created by Sony and Lucasfilms, which is often used in movies and for some other stuff. So in my pictures, you see this Mario example. Mario is, in this case, he's just 3 frames that are cycled between. In 3D, like in the newer Mario games, they don't actually do geometry caches, but imagine that you save the mesh for every frame of this cycle, and then you cycle between the meshes. That's what Alembic or a geometry cache will let you do. There is this Unreal video.
And, I've got this cool little or water-looking mesh, so I'm going to go ahead and...
In this case, they baked the liquid animation into
and if I go ahead
an
and
Alembic
hit T on my
cache that
keyboard,
Unreal is
you can
reading.
see I've got this cool little water simulation. Looks like, coffee is pouring up through the cup, and then it's... Yeah, it's very dark.
The benefit of baking it into an animation is that you don't have to do the physical simulation real time. And also, as we'll see in a second, liquid animations, for example, are complicated enough that they can't really be described with any other format besides geometry caches. Why does it always do this? Okay. Anyway, some pros of a geometry cache. You can represent any arbitrary animation sequence in 3D because you're no matter what, in some way you can simplify your animation to a frame-by-frame mesh. So you can represent any animation this way. They're very easy to understand, I think at a high level, because 2D animation works basically the same way. They're good as a last resort for animations that cannot be described by any other method, and we'll see these other methods in a second. So for example, physics simulations especially. If you wanted to bake this, for example, into a game, let's say, I don't know, in a video game like Crisis, there are helicopters that fly into buildings and they break all the buildings and stuff like that. That kind of animation can be baked like this. And geometry caches can also describe very detailed animations. So for example, in Star Wars Rogue One, they reconstructed Grand Moff Tarkin as a, most people noticed that it didn't look that natural, but even so, it was still a very natural looking character. There were some things that were off. There was definitely an uncanny valley thing, but that was a really detailed animation. And they probably used a geometry cache, also because it's Lucasfilms, and they made the format. So another example of physics animations. In this example, what this guy did was he baked some physics animation in Blender. So he has this cloth that falls down and wraps around the cylinder, and he's trying to export it to Unreal. So it exports as an ABC file. Where is the animation? I guess we'll see it in a second. Oh, there it is. Yeah, so he's trying to send this animation, this physics-based animation, to Unreal. So he bakes it into an Alembic file, and then when you import it into Unreal, you know, it will be, there's already support for Alembic caches, so you could play this baked thing into inside of Unreal. See? So here's just an example of the usage. Okay, YouTube. Some cons of geometry caches. They are pretty slow at runtime, actually. They require you to have a couple of, you know, really fast things. For example, on a typical hard drive, it would be really hard to switch between meshes. Meshes are much bigger than a single frame of a movie. So swapping between meshes is not particularly easy. You know, there are considerations about whether you should do it on the GPU, or, you know, where you should store the data while it's being swapped between, and things like that. Generally, if you don't have a good SSD, if you don't have a good GPU, then a geometry cache is simply not feasible. They're really, really resource intensive. So for example, I'll show you this video in a second, but we made this 1-minute animation that took 40 gigs of RAM and 80 gigs of disk space to run. They were reconstructing this person in our lab. I'll show you the Fred Brooks one, actually. It doesn't look great, but you know, the results are weird. It's reconstruction, I mean, it's hard anyway. But what they did was they reconstructed the front of Citizen, and she is giving a tour.
Carolina Inn Hotel. Department members sometimes hold lunch events and meetings in its restaurants.
But anyway, they were trying to reconstruct her face motion and leg motion and arms and things like that. And, you know, it's a relatively simple animation. I mean, it is reconstructed, which makes things harder, but it is a relatively simple animation, but it took so many resources. So you need 20 gigs to describe each mesh frame. So each frame in our case was 20 megabytes, which is actually way bigger than most meshes in games will be. But in any case, then you need another 20 gigs to describe the baked Alembic animation. So Alembic will still store basically every frame at the same detail. It's just that Alembic as a file format also has information about how to switch between them. There is, when you import it into the game engine caches things. So for example, Unity has .meta files, Unreal has .uasset files. And finally, there is some cached versions. So for example, Unreal will cache things a second time in the intermediate folder. Unity puts them in the library folder, as many of you noticed trying to move your projects between computers. So tons of disk space. And game engines didn't support it for a long time, which means that older games simply can't do this anyway. And it makes sense. I mean, all the resources, I mean, it's just, we don't use geometry caches unless we absolutely need to. They tend to be a last resort for things that are pretty much impossible to describe otherwise. So obviously, geometry caches are not a great option for game engines, because game engines expect that you can run at a certain frame rate and on a certain, you know, a certain set of devices. So there are some important optimizations that came about. So generally, we'll stick to keyframe-based methods, which I'll explain in a bit, for the individual animations. And we interpolate or blend between each animation that the person is capable of doing. So the walking, the running, the crouching, crawling, whatever they're doing. And we'll talk about these separately. So to mention keyframes first, or to explain keyframes first, keyframes are just frames of the animation that you designate as causing some sudden change in the transformation. So, for example, with this cube animation, there is some initial keyframe where it's in this pose, and somewhere over here, probably at frame 20, there is a keyframe that describes the cube as being over here somewhere, and you interpolate between these two frames. There are a couple of different interpolation methods, so you can interpolate linearly, you can use a sine function. This will just describe, it'll describe how fast it moves along the timeline. So for example, this one is pretty much linear. Notice that there's pretty much a one-for-one correspondence between the person moving the slider and the cube moving. If this were a sinusoidal function, maybe the cube would move really slowly in the beginning, then it would speed up, and then it would slow down again. So there are a couple of different ways to interpolate. I'll show you an example in Blender. Of course, this requires me to stop streaming Chrome, and I'll stream my screen again. Go live. Screens, the screen. Can you see my screen again? Hello?
Yeah, we can see it.
Yeah,
Cool.
yeah.
You can see like the Blender window and stuff. You see Blender? See
Yeah,
Blender? Cool.
Yeah, we
All right. So if I have my monkey, and I want the monkey to have some if I want the monkey to do a really really simple transformation, what I would do is Blender has, for example, the details of Blender are not important here because you won't be doing animation in Blender, hopefully. I mean, it's up to you. I actually think Blender's animation API is pretty good, but Blender has some available keys. You're probably getting nightmares from assignment 3, but you have some types of keys. So for example, you can store all of location, rotation, and scale. So I can hit I to create a keyframe here. Blender has this thing called a dope sheet, which, you know, it's describing in frame 1 what these values are. And then let's say that in frame 30, I wanted to move over here. I'll key that, and I can interpolate between them. Now let's say that I wanted to also rotate. RZ. Let's say I wanted to rotate like that. And it's interpolating both the translation and the rotation. And I can do the same thing for scale. So like this, key this again, and it will do all three of them at the same time. And I can copy this keyframe, for example, and let's say that at frame 60 I want it to go back to its original animation. I can just paste the set of keys again, and what it will do is it will go to this keyframe, and then it will go back. And so I have this animation, and you know, if I were to set the end to be 60, and I played it, it would keep looping, I think. So, you know, I think keyframes are relatively simple to think about. They're pretty common. Anybody have any questions about keyframes? I don't think they're too bad. I mean, this is the most common way of animating, I think, by far, in both 2D and 3D. Let's see. We don't have much time left, but yeah, we don't have enough time to talk about the next slide. But next time we'll talk about, we're going to keep going deeper into animations. So we'll talk about blend shapes, which are these cool animations that can describe things like facial animations. The effects themselves are really weird, but you can do really cool things with them, like lip sync and stuff like that. And you can make really detailed animations, like notice that her chin crunches up. That's really hard to do with any other kind of animation method. So, yeah, let's say that's it for now. Does anybody have any questions? All good. Cool. Assignment 7 and the midterm proposal are due Friday. The midterm assignments will be due Monday night. I didn't change the Sakai deadline yet, but it will be Monday night because of my policy that things should be due at the end of a class day. That's pretty much it. You're free to go. Bye.